Hi, folks. Today we're going to talk about probability. And so, what is probability? When we define mathematics, we defined it as the study of absolute certainty. Probability, in many ways, is the exact opposite about that. It's a tool for measuring uncertainty. And so, whether we define probability as mathematics or mathematics adjacent, what is clear, though, is that it uses a tremendous amount of math. And so, classical probability focuses on the ideas of discrete math and combinatorics, while as other forms focus on measure theory and calculus. But there are a number of other things which pop up when we're talking about probability. Really, it's borrowing heavily from all of the different math we've talked about throughout the semester. And so, probability fundamentals. Let's just talk about what the basics are before we jump into anything real. So before we begin to calculate probabilities, we need a clear idea about what it is that we are actually measuring. And so an experiment is the process by which an observation or measurement is obtained. An event is a possible outcome of an experiment. Two events are mutually exclusive if, when one event occurs, the other cannot, and vice versa. And so as an example, suppose in a class of 20 students, we wish to consider their midterm scores. This could be considered an experiment. An event could be that there are at least 12 A's on the midterm. An alternative event could be that there are 12 B's on the event. These two events would be considered mutually exclusive because they can't both happen at the same time. We don't have 24 students. And so, with that idea, the probability P of an event E is a measure of the likelihood of an event occurring. It's denoted by P of E, where E is some event. The values of a probability can vary from 0 to 1. A probability of 0 is seemingly impossible event. Usually it is impossible, but there are occasions. While a probability of 1 is almost certain. Again, usually we think of it as certain, but there are some weird exceptions. And other probabilities can be thought of as a percent. And so if we are at 50%, that would mean that there is an even chance. If something is greater than 50%, then it's going to be more likely. If something is significantly less, then it's going to be unlikely. Now, there are standard ways to denote the probability of an event. One, the simplest, is a fraction. And so you see this most commonly in discrete probability, where we can see the possible simple events. The second one is as a percent. And so this is used for both discrete and continuous probabilities, with 0% being highly unlikely and 100% being almost certain. And then 3 is as odds. And so the odds of an event occurring is typically written as a ratio comparing the event occurring to it not occurring. 50% would be written as 50-50 or 1-to-1. A 75% likely event would be 3-to-1. And if the probability is 1/6, like for a 6-sided dice, we could write that as 1-to-5. Another thing to note is when we're thinking about these probabilities, it's never a guaranteed thing because we're dealing with uncertainty. And so when we think of a 75% probability, it doesn't mean that out of every 4 experiments, 3 of them are guaranteed to be your given event. Probability is uncertainty. It's possible that you could have something which has a 75% probability, but still get 20 in a row which don't match our event. Instead, when we're thinking of probability, we want to think of the law of large numbers. The law of large numbers states that the probability of an event occurring reflects what would occur if an experiment were repeated a large number of times. And so upon repeating a coin flip millions and millions of times, we would expect to see roughly 50% heads and roughly 50% tails. That doesn't mean that we won't get a string of 50 which are all heads. It's unlikely, but it happens. Unlikely events happen all the time. With this, we're going to introduce a couple more terms. And so some events can be broken down into simpler events, which are mutually exclusive. We say that a simple event is an event which cannot be broken down into simpler events, or simpler mutually exclusive events. The sample space is the set of all possible simple events. And we sometimes define an event as a collection of one or more simple events. As an example, think of dice. Suppose that you roll a six-sided die. An event could be observing a number less than 4. Well, this is not a simple event because it could be broken down into 3 mutually exclusive simpler events: observing a 1, observing a 2, and observing a 3. Each of those is a simple event. You can't really break down observing a 1 into 2 different things. The sample space would be the 6 outcomes of observing each value. There we go. Types of probability. And so there's 2 standard types of probability. There's classical probability and there are probability distributions. We'll touch on probability distributions, but we're mostly going to focus on the classical probability. Classical probability involves measuring the likelihood of discrete events, experiments which have some finite number of equally likely simple events. For example, rolling a 6-sided die where each side is equally likely. Discrete math and combinatorics is usually sufficient for classical probability. The other option is probability distributions. Probability distributions involve measuring the likelihood of an event occurring when there is either an infinite number of events or things are not equally distributed. For example, pick a real number between 0 and 1. What is the likelihood that the square of that number will be between 0.4 and 0.5? Well, there's an infinite number of possibilities there, and so we can't use our classical approach. Often we need a little measure theory or calculus to fully understand probability distributions. And so let's go to the classics. What are the classic experiments which we will be focusing on? The first one is flipping a coin. And so there are many tools which we use. The simplest is a coin. A coin typically has 2 sides denoted as heads and tails. We can flip it in the air and then when it lands, determine whether it is heads or tails. A common experiment is flipping a coin some number of times. And so events involved counting how many times you get heads or tails. For example, I flip a coin 5 times. What is the probability of getting heads 3 times? That would be a standard event that we would be looking for. Another one is rolling dice. And so a die, plural dice, is an object which can be rolled, and it will display a different number or symbol when rolled. Most commonly, we deal with 6-sided dice, which has the numbers 1 through 6 on its sides. Common experiments involve rolling some number of dice and adding the values together. We see this in popular casino games like craps, but folks have been rolling dice for over 5,000 years. We do not even know how long dice have been around, but it has been a very, very long time. Another experiment is cards. And so while there are many types of cards in introductory probability, we often focus on the standard 52 card deck, which is displayed on the screen right now. We have 4 suits: clubs, hearts, spades, and diamonds. Clubs and spades are black, hearts and diamonds are red. Each suit has 10 number cards and 3 face cards. The ace represents 1 or sometimes 11. And then we have 2 through 10. And then for the face cards, we have a jack, a queen, and a king in each suit. Occasionally, we also include additional cards, which are known as jokers. Another common experiment is roulette. Roulette is a game of chance in which a ball is rolled around a spinning circular track until it eventually settles on a number. The numbers range from 1 to 36, each colored red or black. There's also 1 or 2 green values of 0 and 00. It depends on if you're playing in European roulette or American roulette. Events which individuals place wagers on include red, black, green, evens, odds, individual numbers, or groupings of numbers. In the casino game, each has a different payout. But really, we can think of this as having 37 or 38 different outcomes, depending on which version you're playing. Classical probability. Let's do some applied combinatorics. And so before we begin calculating probability, we can attempt to estimate it. Suppose we observe an experiment a large number of times and count the number of times an event E occurs. Based on the result, we can estimate the probability of the event. It's the number of times the event occurred divided by the number of times the experiment was run. While just an estimate, sometimes this is the best we can do. And here's an example where this is the best we could do. Suppose you go to the beach every day for 4 weeks and you see a sea otter on 17 different days. Well, we can estimate the probability of seeing a sea otter on a given day as 17 out of 28, or 60.7%. In this case, it would not be easy to mathematically calculate an exact probability, and so an estimate will have to be sufficient. So now let's get to the actual probability. And so suppose that an experiment has n different simple events and that each of those simple events is equally likely to occur. This is what we usually see in classical probability. If event E can occur in S of these n simple events, then we calculate the probability of E as the probability is the number of ways E can occur divided by the number of different simple events. And so it's S, which is the number of possible events, or the number of times E could happen, divided by the total number of possible events. Note, the sum of the probabilities for all simple events must be 1. So let's see if we can calculate some stuff. Example, dice. Suppose that you roll a 6-sided die. What is the likelihood of getting a 3 or higher? Well, in this case, there are 6 simple events, 1, 2, 3, 4, 5, 6. Of those, our events of getting a 3 or higher include 4 simple events, 3, 4, 5, and 6. As such, the probability is 4 out of 6, or 66.7%. Let's try. A roulette wheel includes 18 red values, 18 black values, and 2 green values in this case. What is the probability of getting a red value? Well, there are 38 possible outcomes, 18 of which are included in the event observing a red value. As such, the probability is 18 out of 38, or 47.4%. Here's another one. Suppose that you have a standard deck of 52 cards. If you select one card from the deck, what is the likelihood of getting a red face card? Well, if we look, we can just count them up. And so there's 52 total cards. The number of red face cards are 1, 2, 3, 4, 5, 6. And so the probability is 6 out of 52, or 11.5%. Now, combinatorics, we already know, is the study of how to count things, and it becomes very important when calculating events. It's important to use the addition and multiplication rules. When does order matter? When does repetition matter? When is something a permutation or a combination? These types of questions become important as we try to calculate more complicated situations. For example, over here, we have poker hand probabilities, and you can see all of the different possible outcomes. Suppose that you roll two 6-sided dice and add their values together. What is the probability of getting a 7? Well, what we would want to do is we would want to list out all of the possible combinations. And with 2 dice, there's going to be 36 different possible outcomes. And here we can see them. So for the first die, it could be 1 through 6. For the second die, it could be 1 through 6. That creates 36 possible outcomes, of which we can see that there are 6 of them, which are our particular one of interest, getting a 7. And so since there are 6 out of 36, we would say that is 16.7%. Here's another one. Suppose that you selected 2 cards from a standard 52-card deck. What is the probability that both cards are aces? Well, there's a few different ways we could think about this. There are 52 possible outcomes for the first card, but after we've selected a card, there's only 51 possible outcomes for the second card. That means that there are 51 times 52 total outcomes, which means 2,652 possible outcomes for selecting 2 cards from a deck. For our event, there are 4 possible outcomes for the first card because there's 4 aces. But after we've selected one, there's only 3 possible outcomes remaining, which means there are 12 possible outcomes. And so therefore, the probability would be 12 out of 2,652, which is about 0.452%. It's not likely, but it happens. An alternative way to calculate this is to multiply the probability based on each card. And we'll see how we can multiply probability like that very soon. Compound events. And so a compound event is an event combining 2 or more simple events, typically through an and or an or. For example, given a standard 52-card deck, what is the likelihood of picking a card which is both red and a face card? Or what is the likelihood of picking a card which is red or a face card? Well, those are going to have very different answers. In a 52-card deck, there are 26 red cards, there are 12 face cards, and 6 cards which are both red and face cards. And so the probability of being red and a face card would be 6 out of 52. The probability of being red or a face card, well, we have 26 reds and 12 face cards, but there's 6 which are both. And so we could add the 26 and 12, which would give us what would that be, 38? But we'd have to subtract the 6 because we would be repeating those values. And so that would give us 32. And so 32 out of 52 is the probability of being red or a face card. And so this gives us the addition rule. When calculating probability of a compound event, we can use this formula. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. This is what we used in the last example, where we said, well, we have some amount of overlap. And that's what the P of A and B is. That is the overlap between the probability of A and the probability of B. And so here's an example. What is the likelihood of rolling a 20-sided dice and getting a number which is even or divisible by 3? Well, the probability of getting an even number would be 10 out of 20 because there's 10 even numbers between 1 and 20. The probability of getting a number divisible by 3 would be 6 out of 20 because you could get 3, 6, 9, 12, 15, or 18. The probability of getting a number which is both even and divisible by 3 would be 3 out of 20 because you could get 6, 12, or 18. And so using this formula, we would say the probability of A or B, so the probability of getting something which is even or divisible by 3, would be the probability of being even plus the probability of being divisible by 3 minus the probability of being both. And that ends up giving us 13 out of 20. Conditional probability makes things a little bit trickier. And so when trying to determine the probability of A and B occurring, we must be careful about whether the events A and B are independent events or dependent on one another. And so independent events do not affect their probability of one another, while dependent events do affect the probability of one another. We can denote that event B is affected by event A by writing it as this, the probability of B given A. We call this a conditional probability. And so here's an example. If we select two cards from a deck, what we select as the first card will affect the probability of what we select as the second card. If we choose an ace first, then there's only 3 aces left. As such, these are dependent events. If instead we select a card, put it back in the deck, and then select another card, these two events would be independent of one another. You could get, or there's 4 aces back in the deck in that situation. So, given two events, A and B, the probability of A and B both occurring is given by P of A and B is equal to the probability of A occurring times the probability of B given A. And so if the events are independent, we can just multiply without having to worry about conditional probability. If the events are dependent, we have to determine how the products are related. And so let's go back to our pulling aces from a deck. To find the probability of selecting 2 aces from a deck of 52, we can calculate the probability of getting the first ace and the probability of getting the second ace. And so the probability of getting an ace from a deck of 52 would be 4 out of 52. For the second ace, well, now there's only 3 aces left and there's only 51 cards left. And so that would be 3 out of 51. Multiplying, we get the total probability as 4 over 52 times 3 over 51, which is 0.452%. Practice problem. Suppose you flip a coin 3 times. What is the probability of getting heads, then tails, then heads? Alternatively, what if instead we are simply looking for the probability of getting heads twice and tails once? We don't care about the order. For small probabilities like this, usually just create a table. And here's our table with all of the possible outcomes. And so by the multiplication rule, we're looking for one outcome, and every single time we have 2 possible outcomes. So it's going to be 1/2 times 1/2 times 1/2, which is 1/8. For this other one, though, this is going to be a little trickier. And so looking at the table, we can see all of the possible outcomes. If we are looking for the ones which are going to be heads twice and tails once, well, we have heads, heads, tails. We have heads, tails, heads. And then we have tails, heads, heads. And so there are 3 outcomes, which are heads twice and tails once, out of 8 total. And so the probability is 3 out of 8. Let's play roulette. Suppose you are playing roulette with 2 greens and wish to pick the number 21 and stick with it for 2 rolls. What is the probability that you will win exactly 1 time? Well, the probability of winning the first time, but not the second time, would be P of A is equal to 1/38 times 37/38. And so this would be the 1 out of 38 that you got it, or that you rolled the 21, and then 37 out of 38 that you didn't win. The probability of winning the second time, but not the first time, is the same thing. You just flip the 37 and the 1. Since these are independent events, we can just use the addition rule to calculate the total probability. And so we'd say it's the probability 2.56 plus the probability 2.56. We get a total probability of 5.12. And so now, suppose you're playing roulette with 2 greens, and you wish to pick the number 21 and stick with it for 15 rolls. Well, what is the probability that you will win exactly 1 time now? It's similar. And so the math we're going to do is going to be the same. The probability of winning the first time, but not winning the remaining times, Well, that's going to be 1/38 that you got it the first time. And then we're going to say you're going to get it, or you're going to lose 37 out of 38, or you're going to lose 14 times in a row, with each of them having a probability of 37/38. And so 1.81%, that's the likelihood of getting it the first time and then not getting it the rest of the time. But there are 15 such independent events. Because you could get it the first time and none of the others, or you could get it the second time and none of the others, or the third time and none of the others. All of these different cases would be where you get it once, or you win exactly one time. And so 15 times that 1.81 ends up giving us 27.2%. All right, let's talk probability distributions. And so probability on continuous variables. This will be a little bit different. The classical, we could just say, hey, these are the total number of outcomes. But now the total number of outcomes might be infinite. And so suppose that you are asked to choose a random number between 0 and 1. What is the probability that the square of the number will be between 0.4 and 0.5? This problem is different from the preceding examples. There are an infinite number of values between 0 and 1. And so we can't just divide by infinity. Instead, we need some new tools. And that's where the measure theory and the calculus and all those other things are coming into play. In this case, we can't calculate things based directly on the interval. But rounded to the thousandth, any number between 0.632 and 0.707 will give you a number between 0.4 and 0.5 when squared. If you're not sure where those numbers came from, I just square rooted. And so if you take the square root of 0.4, you're going to get the 0.632. If you take the square root of 0.5, you're going to get the 0.707. And so anything between these two values is going to give us our desired outcome. This interval is length 0.075. And so when we subtract 0.707 minus 0.632, we get 0.075, while the total interval from 0 to 1 is 1. And so our probability is this 0.075 divided by 1, which is 7.5%. The idea of considering the intervals becomes the key. And so instead of saying these are all of the possible values, well, now there's an infinite number of values and we need to actually be able to measure the intervals. Some key terms. And so a random variable is a variable x that has a single numerical value determined by chance for each outcome of a procedure. These variables can be discrete, like roulette, or continuous, like selecting numbers on an interval. A probability distribution is a graph, table, or formula that gives us the probability for each value of the random variable. So here's an example. Suppose that x is either 1, 2, or 3, but they are not equally likely. Let's say there's a 20% chance that it's 1, a 30% chance that it's 2, and a 50% chance that it's 3. In this case, the random variable is x, and it is discrete because there are 3 possible outcomes. We can visualize this using a histogram. And so sometimes we use histograms or bar charts to represent the probability distribution of an event. We use histograms to convey data, but we can also use them to demonstrate probabilities. And so here is the previous example. The likelihood of getting 1 is 20%. The likelihood of getting 2 is 30%. And the likelihood of getting 3 is 50%. How else can we analyze this? Well, there's a couple other big ways. One is the mean. And so the mean or average of a set of numbers is the value you get when you add all of the numbers together and divide by how many numbers you have. The expected value is a weighted mean. And so we take values x, multiply their probabilities, and then add them together. If we run the experiment a large number of times, we would expect to get this value on average. And so thinking of the example we just did, Let's say that we have something which is 20% chance that it's 1, 30% chance it's 2, 50% chance it's 3. Well, the mean of 1, 2, and 3 is 2. That's great. That doesn't really tell us a lot. The expected value would be given by 0.2 times 1 plus 0.3 times 2 plus 0.5 times 3, which is 2.3. Well, in this case, that's telling us that we're likely to get numbers which are a little bit or between 2 and 3 in this case. And so we're going to get things which are larger than the mean. And so 2.3 is larger than 2. We would expect on average to get values greater than or equal to the mean. In the case of a continuous random variable, instead of a histogram, we will have a curve which represents the probability density. And the probability density is telling you within some given region, what is the probability of an event occurring? To figure out the probability, we have to select a range of values of x, and we can then determine the area under the curve on that range. To do this right, you need calculus. A little bit of calculus, a little bit of measure theory. That's where it's all coming into play. Of note, though, what happens if we just take the probability of a single instance? And so if you choose a random number between 0 and 1, what is the probability that it will be 0.5 exactly? It turns out the probability is 0%. Because there are an infinite number of numbers on the interval from 0 to 1, the probability of getting any individual one of them is 0%. Of note, it's still possible to get 0.5 when choosing a number between 0 and 1. It's just that the likelihood is 0%. 0.5 is a member of the sample space. It's just that there's so many possible outcomes that it is all but impossible to randomly select it. This is the measure theory idea of of measurability of a set. An individual point is a measure zero set. And so in this case, the likelihood of getting 0.5 out of an infinite number of possibilities is 0. Final thoughts. When we think about probability, it gives us a way to understand uncertainty. We can understand when something is nearly impossible and understand the likelihood of unlikely events. The probability presented here, though, is just the briefest introduction, but it prepares us for understanding the uncertainty of the world around us. Probability, I mean, there's classical, and then there is the distributions, and there is a lot of stuff that you can talk about related to it. There's a reason why statistics is its own field of study, and probability is a fairly decent sized portion of it. The tools of probability and the tools of statistics have a fair amount in common. With that, I'll let you get to work exploring where you find uncertainty in the real world. Good luck, folks.